Hi Bobby.
Hi Aniruddhan.
So we come to the end of another course.
Exactly. A very important course.
Yes, I think this electrical and electronic circuits, no? It's going to we have laid the foundation
Yes,
for
yes.
a whole bunch of concepts
Exactly.
which they will be using again and again and again,
Yeah.
I think, in their career.
In various courses.
Correct.
Various future courses.
Correct.
Analog, even
Yes.
digital,
That's right.
sensors,
Sensors,
system design,
system
various
design,
courses.
control engineering,
Right?
and including some theoretical courses as well, no? So signals and systems.
Yes, yes, yes.
A lot of things that we have taught is going to be useful in a future
Yes, yes.
semester for that.
Certain things are going to be repeating also.
Correct. Correct.
That way it is good.
Correct. That's right. That's right. So broadly, I think we started off with AC circuits.
Yeah.
In a last term in the previous electronic systems thinking and circuits.
Yeah.
What we had done was we had introduced them to AC because they did low pass filter and so on.
Correct.
We did some sinusoid, but
not very systematically.
Not very systematically. We did everything in the time domain.
Yeah.
Right, in many ways. Frequency domain analysis, this is the first time they understood.
Yes.
And we taught them some easy technique, no?
Yeah.
To imagine the sinusoid as a vector which is rotating at some speed.
Yeah. Yeah.
Right. Then you can just take a snapshot of that.
Yeah. And in fact, that phasor concept is relatively new for them.
Correct. And it made things very easy. No?
Correct.
What we did last time was solving differential equations. If you had an input sinusoid, we kind of just solve the differential equation.
Lot of work.
And the minute you do this, it becomes a complex number. Everything becomes a complex number.
Yes.
The complex numbers, students know about it from high school.
Correct.
Right, nowadays.
Correct.
So it's very easy.
Yes. In fact, we have also seen other circuit analysis portions. We have kind of revised the nodal analysis, mesh
analysis. Correct.
Thevenin actually we went a bit deep. And
that's correct.
Norton.
Thevenin, Norton. And we did it for both DC and AC.
Yes.
Right?
Yeah.
In both the typical DC steady state as well as the phasor domain.
Yes.
Complex number domain. Correct. So that we did. And we taught them a few theorems, like you said. Thevenin's theorem, Norton's theorem, then maximum power transfer.
Yes.
Right?
Correct.
It's a very useful theorem.
Correct.
In practice. Correct. And we kind of taught them how to find the Thevenin equivalent.
Yeah.
Given the network at any point.
Yes.
Right. Correct. And we solved some problems as well in all of these for both DC and AC circuits.
Yes. That source transformation.
That's right.
Yeah.
That's right.
Very, simple but very powerful techniques.
Correct. And in fact, on the circuit side, electric circuit side, all these theorems, actually when we did those examples, we showed them that there are probably 3, 4, 5 different ways to solve every problem. Right? You can apply Thevenin's, you can apply source transformation, instead of just blind, of course, mesh analysis, node analysis, you can always use. But if you're interested only in 1 or 2 currents or 1 or 2 voltages, sometimes doing source transformation is a much faster way.
Yeah.
Right?
Correct.
We saw that.
Correct.
We saw that. Correct. Then I think we taught them dependent sources for the first time.
Yeah. Correct.
Right?
Yeah.
So that was very new.
Yeah.
I think so far they knew voltage source, current source.
Yeah.
Right?
Dependent was something new. And I remember finding the Thevenin equivalent resistance or impedance was not that obvious for the circuits with dependent sources.
That is true.
So we have injected 1 ampere and looked at the voltage across.
Correct.
It was actually very nice.
It is very nice.
Yeah.
That's true. And I think we looked at some specific structures, topologies as well. I think we took a star and a delta.
Correct.
And there are converted from one to the other.
With the assumption that both consume same amount of power.
That's correct. And if you do that, in one case there is one additional node.
Yeah.
The star has one additional central node, which the delta has not.
Yeah.
But from the rest of the network, same voltage, same current.
Correct.
Right?
Correct.
At all the other 3 nodes.
Yes.
And That was actually later on in the course also we used that.
Yes.
Right.
Yes.
Star delta transformation.
Correct.
It is useful in many.
Correct. Correct. Analyzing some circuits.
Analyzing some circuits.
Even in the future, I'm sure in the practical applications.
Correct.
We will find it useful.
You will find it useful. Correct. So that was the circuits portion. Then we took almost a 90-degree turn into theory.
Correct.
We taught them something called a Laplace transform.
Yes.
I think so far in the circuits courses they have been looking at
Analysis.
voltages, currents, analysis.
Correct.
But suddenly this thing came new, no?
It transformed.
Correct.
Yeah.
So that was, I would say, much more analytical.
Yeah.
Lot of mathematics, right?
Yeah.
But at the core of it, it is very simple, no?
Correct.
Right? You are doing an integration.
Yeah.
To convert from the time domain, right?
To Laplace domain.
Right? And you can go back and forth.
Yeah.
Under specific conditions, you can do all kinds of useful things, right? And typically those conditions, from the point of theory, we didn't go into many of those conditions.
Correct.
Because most of them are valid for real circuits, which you build with R, L, C, voltage source, current source, right? So there are specific cases where they will be violated, but many of the circuits that we learned here, they didn't violate at all.
Actually, we have touched only the points that are relevant for the circuit portion.
That is correct. Yeah. That is correct. So, absolutely.
And once we know the transform pairs, life is very easy.
That is right.
Although getting the pair for the first time is a little bit of work.
Correct. After that, it's kind of
correct.
Very straightforward. And just like you learned KVL, KCL, and learned to use them to solve circuits. Similarly, once you know these Laplace transform pairs, you can use it to solve circuits also.
Exactly.
Right?
Exactly.
And you can get, you can find out what the current will look like in the time domain, what the voltage will look like in the frequency domain.
Yeah.
All these things become, once you do more and more of this, it becomes very kind of very useful to use in many cases.
Exactly. In fact, that understanding later led to our transfer function.
That's correct.
And then Boby plot.
And then Boby plots and so on. Kind of. So you're right. We kind of revisited that again.
Correct.
At the end of the course.
Correct.
That's right. So Laplace transforms kind of gave us, any mathematical operation, any circuit can be looked at in the Laplace domain. So if you have a specific voltage or current in the time domain, you can look at it in the frequency domain. If you have a component like a capacitor or an inductor doing a derivative function or an integration function, that can also be transformed in the Laplace domain. So it is basically useful for looking at a wide variety of circuits.
Yes.
Right. Then we did another 90-degree turn, right? Almost 2 90-degree turns.
Yeah.
We came back to circuits.
Correct.
Right.
Devices actually.
Yeah. Because we had looked at resistors, capacitors, inductors, but we now wanted to look at new nonlinear circuits.
Exactly.
Right. And we started with the diode.
Yeah.
And that is where that electronic circuits comes in.
Yeah.
Right.
Where we actually used all other previous information, previous things that we have studied. Although Laplace transform we did not use much, but I will use this in the coming courses, I guess.
That is correct.
Yes.
That is correct.
So devices, diode, then we have looked at the clipper, clumper, rectifier.
That's right.
That.
So
all
application
nonlinear
circuits, all kinds of circuits, no?
Yes.
That's right. So we looked at clippers, clampers, voltage doublers.
Exactly.
Right? So we looked at all kinds of circuits. How to analyze, with an ideal diode characteristic, you can get a lot of, understanding about the circuit.
Yes.
You don't need to look at the details of what is the saturation current, what is the exponential curve.
Correct.
Right?
Yeah.
And we learned how to convert AC to DC.
Exactly.
Right?
Yeah. So first we did unidirectional and then we passed this through a low pass filter and then get almost DC.
Correct. That's right. So in fact, I think in the PAD lab course, they are learning to do that as well.
Yes.
Right?
Yeah. Half wave and full wave.
Half wave and full wave rectifiers.
Yes.
Correct.
Yes.
Correct. And after that, I think we went on to more complicated nonlinear devices.
Exactly.
Which is the transistor.
Yes.
Right? I think that's the first time they must have heard this term before,
Yeah.
maybe even seen a
Yeah.
little bit of it in
Yeah.
in high school. But I think in the electronics program, they're seeing it for the first
Correct.
time.
Correct.
So
So there we have seen, I mean, in fact, quite detail,
that's right. That's right.
various configurations. I mean, first we looked at how mathematically it can be represented, current and voltage. Then various bias conditions, configurations, common emitter.
Correct.
Mostly we have seen. We have seen the other
The
configurations
other
also.
ones as well. In fact, we looked at current mirror,
Yes,
differential
yes, yes,
amplifier,
yes, yes.
right? We looked at a lot of
Yeah.
interesting circuits.
Common mode rejection
Common
ratio.
mode rejection. That's right. So
That way, it's very good course.
it's a very good course. Correct. So, and we also looked at what happens with DC and what happens with AC as
Yes,
well.
yes.
So we learned when you apply a very small sinusoidal signal, how to understand and analyze the circuit.
Small signal,
Small signal. Correct. Correct.
transconductance.
Transconductance.
Probably that's a new term.
That's a new term they have learned. Small signal gain.
Yes.
Correct. So then we also looked at the transfer characteristic.
Yeah.
Right. We took one of these common emitter and plotted the transfer characteristic.
Yes,
So you
yes.
take a DC voltage, give it at the input, change it from maybe lowest value that it can accept to highest value.
Correct.
What happens to the output voltage?
Yes. Yes.
Correct.
Then we moved on to
The
MOSFET.
another correct.
Yeah.
Another type of transistor.
Correct. Correct.
The MOSFET.
Correct.
That's right. So I think in that the MOSFET, so the BJT was somewhat connected to the diode because the characteristic was still exponential.
Yes.
For the first time, and that made things a lot easier for us. For the MOSFET, it's a square law relationship.
Yeah. Yeah.
So you have to calculate. You can't assume that the voltage is 0.7 like you did in the BJT.
Yeah.
So you have to calculate it every time.
Correct.
So we learned how to do that. We learned how to do biasing. Again, small signal, we learned different kinds of structures, transistor amplifiers.
Good thing was no gate current, while BJT always draws some
That is
base
correct.
current.
That is correct. So that is the big difference. And we looked at one very important circuit,
Yeah.
which is the inverter,
Correct. Correct.
right?
Correct.
The CMOS inverter.
Exactly. Exactly.
Correct. So that really kind of
Gave a full picture of.
gave a full picture of all the techniques that
Yes.
are
Yes.
used.
Yes.
And really that ties up electronics with digital.
Digital.
side,
Yes. Yes.
right? So that is kind of the basic building
Building
block
block.
of digital systems. That's right. So, and of course, we came back, to circuit theory. We talked about two-port networks,
Yes.
Z parameters, right? So from electronics, so again, we came back because two-port networks, it's good to give an introduction because it can be used to study also transistor amplifiers also at a
Yes.
later stage,
Yes.
but also to look at passive block like a transformer. We saw a transformer for the first time,
Correct. Correct.
right? So they are also useful for studying regular electric circuits, right? And there are different kinds of ways of abstracting, right? You can have a very complicated network. You can just take, 4 parameters, Z11, Z12, Z21, Z22. You don't need to know what is inside.
Yes.
You can build an equivalent circuit for
Correct. Correct.
the whole network, right? So those two-port parameters were, very useful.
So we have discussed Z parameter and then Y parameter.
Z parameters and Y parameters. And we also told them there are many different kinds,
Correct.
no?
Correct.
Depending on which pair of,
Yeah.
whether you take two voltages or two currents as the independent parameters, or you can take one pair of voltages and one pair of currents, that will give you a different parameter. So you can get several types of parameters. So, and finally in the last week, like you pointed out earlier, we came back to Laplace transforms again,
Yes. Yes. Yes.
Boby plots,
Yes.
looked at understanding transfer functions, what happens in the frequency domain, in the real and imaginary axes.
There, I mean, we have set S. I mean, in the S sigma, we set it to 0 because we are looking at the steady state.
Steady state value. We are looking at what happens when you set S equal to j omega only,
Yes.
not sigma plus j omega.
Yes. Yes.
That's correct. That's correct. So that's kind of a summary of, I think, what we did throughout this course. And now this course is now going to lead to many other
Exactly.
courses, right?
Exactly.
Now I can imagine at least 2-3 courses where this is going to go. For example, signals and systems. I think whatever they have learnt in Laplace transforms, they learnt about delta function,
Yeah.
step function, what happens in time domain, frequency domain. They'll be doing a lot of this in the in the frequency domain.
Yeah.
Again,
Correct.
much more time and frequency domain.
I was just thinking about this gate paper.
Yes,
It covers many topics of,
that's correct.
ECE or EE.
That's correct.
Mostly ECE.
Mostly ECE.
Yeah.
Correct. That's right. And so signals and systems will take forward the Laplace transforms and that kind of material forward, and that is going to be a very interesting course as well. Then, of course, digital systems, if they do digital IC design, inverters and
Correct,
so on,
correct.
CMOS inverter, that will go ahead. That will most likely be an elective.
Yeah.
Analog systems.
Yeah.
So I think some of the material that they have learned
Is very, very useful.
very, very useful, right? Both for analog systems and
Sensors also.
Sensors also.
Yes.
Right? For these two courses, the electronics portion, a little bit of the Laplace transform portion will
Yeah.
also be useful for
Yes.
both these courses.
Yes.
So I think this course is going to lead into
Yeah.
whole bunch of very interesting
Exactly.
courses coming
Exactly.
up, right? So we'll wish the students good luck, right?
Yes. Yes.
In doing well in this course as well as in the follow-up courses.
Yes. And in the future.
And in the future.
And in fact, we enjoyed teaching this course.
Absolutely. And I think this new way of teaching together
Correct.
worked out very well in this
Yes,
course as
yes,
well. We are
yes.
very happy to teach it together.